Okay, I'm going to introduce the dot product. The dot product is extremely interesting and very useful. In fact, an extension of the dot product called the inner product is used in quantum mechanics and in relativity. In general, mathematically, it's defined on more abstract vector spaces, whereas the dot product is used for these kind of geometrical vectors that we're used to, these pointed line segments with magnitude and direction. But if you remember back to our definition of a vector and vector spaces, we said that a vector space was a set of objects called vectors that had just two characteristic properties. The first was that you could add two vectors together and get another vector, and the other was that you could scale a vector, okay, by multiplication by a scalar, and you would also get a vector returned. There's a few other axioms thrown in there as well, but you get the idea. And that definition of a vector is so broad that it includes all sorts of things like the zero vector. It includes operations over the real numbers, over the complex numbers, over the rational numbers. It also includes multi-dimensional space, so Rn. We've been particularly using R2, or two-dimensional space. And in fact, the definition of vectors is so broad that it applies to polynomials. So if you take the coefficients on a polynomial and put them into arrays, they act exactly like vectors. So linear algebra can be used in analyzing polynomials. So it's really quite broad. But for the time being, we're going to concentrate our efforts on the dot product. So we're going to define the dot product in a very particular way. We're going to define it using kind of an arbitrary definition, but one that will make sense momentarily. So if this is the vector v and this is the vector w, we're going to define v dotted with w to be the length of v times the length of w times the cosine of the angle between them. Here's the angle between them, theta. Okay, it seems quite arbitrary, but there are very good reasons. So you'll notice that we are only considering in this definition length and angle. Okay, at no point have I talked about the coordinate system because it's not important. V, that vector v, is the same in any coordinate system. Okay, if we take, for example, the Cartesian coordinate system, I hat, j hat as the basis vectors, you can decompose v into components with respect to that basis, but you could also just as well take some kind of rotated basis vectors, okay, still orthogonal, but rotated in some way, and you would it would just work just as well, okay? Or indeed you can take non-orthogonal basis vectors, for example these two here, and you would also get the same answer. It's a good thing about vectors. They are the same regardless of coordinate system. I'm going to take, though, the easiest case. I'm going to take a Cartesian coordinate basis. But instead of calling the unit vector on the x-axis I hat, I'm going to call it E1. And I'm going to call j hat E2. And the reason is that later on I'll want to use numbered indices here to make our notation more compact. Okay, but even though it's just E with an arrow and not a hat, it's still the unit vector along the x-axis and the unit vector along the y-axis, and it's the Cartesian, the normal familiar Cartesian basis. Okay, so I can take v decompose it into components we'll call v1 times our unit vectors, and w is w1 times e1 plus w2 times e2. Okay. Great. If I now dot v with w, okay, that means I'm going to have, let's see, we're going to have v1 w1 times e1 dotted with e1 plus v1 w2 e1 dotted with e2, okay, plus v2 e2, whoops, v2 w1 e2 dotted with e1 plus v2 w2 e2 dotted with e2. Okay, now because we're using a Cartesian basis, e1 dotted with e2, sorry, e1 dotted with itself, e1, is going to be the length of e times the length of, sorry, the length of e1 times the length of e1 times the cosine of the angle between them, but the angle is 0 because they're the same vector. The cosine of 0 is 1. So you get 1 times 1 times 1, so that's equal to 1. e1 dotted with e2 is equal to the length of e1 times the length of e2, both of which are 1, times the cosine of the angle between them. The angle is 90 degrees. Cosine of 90 is 0, so that's 0. Same argument goes for e2 dotted with e1. That's 0. And e2 dotted with e2. That's 1. So you end up getting here v1 w1 plus v2 w2, which is the other very well known expression for the dot product. Okay, so this, it turns out, this would not be true. You could not multiply the coefficients in this manner if the coordinates, if the basis vectors weren't unit length and orthogonal. You would get something slightly different. It turns out that you also wouldn't get this this very neat answer if you did not define the dot product of v and w with this definition here, the length of v times the length of w times cosine theta. Okay, if you chose, for example, some other product, let's call it v triangle w, where we define that to be the length of v times the length of w with no cosine theta, this would work very well. I mean, it would be an expression that might be useful. Okay, it certainly works as some kind of multiplication between the two vectors, but it it would not result in this neat algebraic answer here that you have with the components. This would not work out so neatly. So whatever way you decide to set this up, you're going to want to include a cosine theta so that you get this neat result. Okay? But this, at the end of the day, this is our actual definition of the dot product involving lengths and angles. It just so happens that if you define it in such a way and you use a Cartesian basis, it leads directly to this result here, which is nice and neat and very handy. And we will look at the next video at a few of the useful expressions that we can derive involving the dot product.